mostly because I think seeing it twice is a good thing. This has got some real basic circuit analysis stuff in it, and we're headed into the circuit analysis chapter, and the big portion of the next test is circuit analysis. So I just want to work through it one more time. I don't know that I'll finish it this time. I know I didn't finish it last time, but I understand. It's kind of at the end with attention spans are dropping and so forth, so let's do it at the beginning when attention spans are up. Number 66. So let's even make up a few numbers. We have a capacitance C1, let's say it's 20 microfarads. And hook it up to a battery and it gets some charge. Let's give it 100 microcoulombs. How does that happen? Well, that happens by hooking that capacitor up to a battery. Say this is a 20 microfarad capacitor and it's got 100 microcoulombs of charge. What was the voltage of this battery? Doesn't say, does it? I hope it doesn't say. No. Did you find out the voltage of that battery? Yeah, isn't capacitance V over V? So V must be Q over C, so it must have been a 5-volt battery. So I hooked a 20 microfarad capacitor up to a 5-volt battery, and that means it got 100 microcoulombs of charge on it. So that's the beginning statement of the problem. A capacitor of capacitance C1 carries some initial charge. And I just made up numbers because it might be easier. Now let's take that charged up capacitor, unhook it from the battery right over here. Once we unhook it from the battery, there is no way to change its charge, as it just sits there. While it's hooked up to the battery, you could do some things to make it have more charge. For instance, you could move the plates apart, and that would change the capacitance, and then it would get more charged or less charged. But once it's away from the battery, the charge that it has is the charge that it has. Until you do something to electrically change that. And now we hook it up to a different capacitance, C2. And let's see, so that should be a known also, since they gave you a letter for it. So this was a 20 microfarad capacitor. Oh, let's make this one be 40 microfarads. What's going to happen? Well, again, there's no way for this positive charge to get to that negative charge. If they could, they'd come together and neutralize each other. We'd have less separated charge. But this is insulated. There's no conductor between this side and that side. But this is a conductor, connecting wire is a conductor, and this is a conductor. So that positive charge can move freely if it wants to. Well, why would charge want to move? Like charges repel. They won't all, I shouldn't take all 5 of those X's and draw all 5 of them down here, because that would just reproduce the problem. We've got a bunch of positive charge crowded together. But it is possible for it to spread out some. So let's take some of these away and put them down there. And likewise here, let's take some of those away and put them down there. The grand total amount of charge is still going to be our 100 microcoulombs. Because I didn't take any of that charge away and put it, off in some other place in the universe and just bring up more charges somehow to it. I just rearranged them is all I did. So I've still got the same amount of charge. Now this was hooked up to a 5-volt battery, but a 5-volt battery and a 20 microfarad capacitor means 100 microcoulombs. This doesn't have 100 microcoulombs anymore, does it? It's got less than that, because some of its charge went to the other capacitor. So its voltage is no longer 5 volts. Let's just pretend to call this the 0-volt spot. You're always free to call 0 volts wherever you want to. just like you're free to call your zero of gravity energy the floor, the tabletop, the ceiling, call it whatever you wish. But that means if you call that 0 volts, then this has to be 0 volts also, because they're connected together. I don't know what voltage number 1 would be, but whatever it is, it would be Q1 over C1, wouldn't it? But that's how voltage, charge, and capacitance relate. It is Q over C. So capacitor 1 is at voltage V1. Whatever that number is not going to change because this is a conducting wire. We did that in lab. We connected a voltage probe across 2 ends of a conducting wire and got what result? Remember? 0. No difference between the 2 ends of the wire. So if this is at voltage V1, so is that one. And that's a big circuit analysis point. The way those things are connected together is called in parallel. And things that are in parallel have the same voltage. That's an important idea to keep, at least to the end of the semester. I'll probably keep it till MCAT's rule, something like that. So the voltage across number 2, which would be Q2 over C1, is the same as the voltage across number 1. So Q2, Q2 over C2. Voltage 2 is Q2 over C2. So these two Q over C ratios are the same. Well, that looks like one equation with 2 unknowns in it, right? I don't know Q1, I don't know Q2. But I know a relationship between Q1 and Q2. Q2 is 100 microcoulombs minus Q1. And I can solve that pretty easily. That's just an algebra equation with one variable on it. Cross multiply, isolate the variable, plug in the numbers, and you could find out what Q1 is. If you know what Q1 is, you know what Q2 is. And if you know what Q1 is, you know what V1 is, and you know what V2 is. And so you completely solve that problem. 2 big points I wanted to bring out was this conservation of charge, that this didn't create or destroy any charge, it just got rearranged. And then the fact that these 2 potentials are the same because of the way that things connect. Some useful ideas that will carry into circuit analysis, which will probably start on Monday. Okay, questions as we work through this? And I didn't finish the numbers, but I think the numbers help you think about it a little bit. All right, one last quick idea about capacitors. I'm not going to preach on this. I'm just going to point it out to you. Our basic formula for how to build a capacitor involved the area of the plate, the distance between the plates, and the material in between. If we're using air or vacuum, then we just plug in that number, 8.85 times 10 to the minus 12. But if we're using some other material, we put another factor in here which tells you the electrical effects of that material. It's called the dielectric constant. And there are a few of them tabulated in the table. What does that do to the capacitance? Makes it bigger. So C just got bigger by putting that material in between the plates. Physically, why does that happen? It's because the material in between the plates gets polarized. In particular, then, the capacitance number got bigger, the amount of energy you can store got bigger, the amount of charge you can store got bigger if you leave this capacitor hooked up to a battery. while you put the dielectric in it, then you can suddenly store more charge. Or if you disconnect it from a battery, the voltage will go down because of that dielectric. Those are just some facts. I just pulled them out of the section of the textbook and thought I'd consolidate it all in one kind of simple place. That's really all I want to say about dielectrics. I don't think the formulas are complicated. I think if you want to do some of the homework problems that involve dielectrics, you can refer to that section, you refer to this, you can probably do okay with it. I promise not to put a required dielectric problem on the exam. There might be an optional one, because this may just seem as simple as anything to you, and think, oh yeah, I can handle that, better than I can handle some other ideas. So I may put this on the test, but it'd be like on the last test, you didn't have to do everything. You won't have to do dielectrics if you don't want to. Okay, that's all I'm going to say. And that, I'm done with that chapter on voltage and capacitance. So we are ready to move on to the next of 4 chapters that relate to our electricity ideas. The first 2 chapters were more, when I say theoretical, more abstract, Coulomb's law, electric force, electric field, electric potential. Now we've started getting a little more practical as we talked about capacitors and energy storage and how they behave in circuits. And then chapter 18 and chapter 19 is more of that, I think, more practical stuff. It will relate very much to what you did in lab on Tuesday and what you'll be doing in lab the next 3 weeks or so, which is all circuit stuff. Well, man, how can it function in the last part? UFIS just felt like they've been beaten to a pulp. Are you guys at that same place? Is it just kind of universal? This is the time? This is the first of several times through the semester. Probably, but you just are a little sorry, I guess we're the cause of that, I suppose. We keep doing it, and you keep graduating, and becoming doctors and physical therapists and so forth, so we keep doing it. So if you just all want to fail the MCAT and wind up managing fast food for a living, then tell us and then we can change what we're doing. Otherwise, it seems like we're not doing something sort of okay. We're not unsympathetic. I don't know that we do a lot about it, but I like to think we're not totally unsympathetic. Okay. Everything that we've talked about with electricity so far, we haven't really paid attention to the motion of the charges. Sure, they moved. There were, in my little picture, there were 5 charges here, and then they rearranged, so there was 3 there and 2 there. But we weren't studying the motion part. We were setting up basically a static situation, maybe making some changes, allowing it to come to equilibrium again, and then studying that new static arrangement. But now we're going to switch and actually start watching charges as they move. So I suppose you could say we're switching from electrostatics to electrodynamics. Often that word is reserved for a little more high-powered physics than what we're doing here, but it's still appropriate. We're watching charge move. So it certainly isn't electrostatics. Well, I think I used this same simple little example back in chapter 4 last semester, but if the book suddenly started to move, what would you think happened? Magic, okay, or at least several hundred years ago, or a few thousand years ago. Yeah, magic. Yeah, a force, probably. Then you'd start looking for, was there a magnet someplace? Did he have a string hidden that he pulled? How did that book start to move? Okay? Changing from static to moving means there was a force. Well, what's perhaps the most common way to make charges switch from static to moving is an electric force. Right? Remember our basic equation that if there is an electric field, and you plop another charge down in the middle of that electric field, that charge will feel a force. Okay? That's just kind of the core definition of electric field. So if there's a moving charge, a charge that started to move or changes its state of motion or something, we would probably assume there's an electric force on that charge. If there's an electric force, there has to be an electric field by that definition. That's how we think about the cause of electric forces, is that some other charges someplace else are making an electric field. But if there's an electric field, the voltage has to be changing. Because electric fields always point from a high voltage location to a low voltage location. If the voltage doesn't change, there's no electric field. So in my mind, all four of those ideas are equivalent. You can say there's a change in potential, or you can say there's an E field, or you can say, oh, there would be force on charges, or you can say, oh, there are charges that are going to move. All of those are basically saying the same thing. Circuit analysis basically exploits the connection between the last two. We'll look at the moving charge potential relationship. Circuits are almost always analyzed in terms of energy ideas, and almost never in terms of force and field ideas. But you kind of need the force and field to understand what the potential is. So that, at least, is the kind of the standard pedagogy. You learn about forces and fields, and then you apply it and start talking about potential, and then you start talking about circuits. First section in chapter 18 is entitled The Electric Battery. It's interesting stuff. Batteries are incredibly interesting things these days. You know, wouldn't it be nice if you could get a battery in your cell phone that only had to be charged once a month instead of maybe every night? Battery technology, an amazing thing. Electric cars. How far can you go? 200 to 300 miles? Most people want to drive farther than that if they're on a road trip. So does that mean you got to stop at lunchtime and find a power station? Well, what if you could get, a better battery and maybe store 1,000 miles, and maybe you go a couple days without a recharge? There's a brand new Boeing something. I think it's 787, but maybe whatever was before that. I don't know if it was in 67 or in 77, but it had a bunch of lithium-ion batteries on board, and they were catching fire. Like the first couple of, I think, trans-Pacific flights, maybe Japan Airlines was one of the first to buy some of those aircraft, and they had a couple of flights with battery fires. What do you do with a battery fire when you're out over the Pacific? Well, I heard of that movie, Snakes on a Plane. Fires on a plane is probably just as bad. So a lot of interest in how do we make a safer battery, and yet a good battery. It's appropriate for what we're going to do with it. So I think battery technology is incredibly interesting. I don't know much about it. So I'd say what little there is in the textbook, you can read it for general understanding if you want to know a little more about batteries and the history. One thing you do need to know, which you should know from lab, a battery is a source of constant voltage, not current, voltage. The idea to keep in mind as we start doing this. So we talked about current last lab. That's where we'll start again today. Current is a rate of passage of charge, but it's not a speed. Because if it was a speed, it would be so many meters per second. It's not. It's so many coulombs per second. If each of you carried a static charge on your body, and then after class you walked out the door, we could figure out, well, how many coulombs went through the door in how much time. It took 30 seconds for you to leave the room, and everybody was carrying 2 coulombs, so there's 30 of you times 2, 60 coulombs in 2 seconds, 30 amperes, 30 coulombs per second was passing through the door. That's the way to think about charge. It's not, it's related to speed, because if all of you ran out the door instead of gently walked out the door, it would change the rate of passage of charge. Okay, so it's related to speed, but it's not speed. Think about maybe mass transfer. Which moves more mass? very fast motorcycle or kind of a slow lumbering 100-car coal train, which is going to move more mass in the same amount of time. The great big coal train, yes, it's moving hundreds of kilotons probably per hour, even though it's going slow. While the motorcycle is moving a few kilograms, 100 kilograms per hour or someplace. So it's not speed, it's rate of charge passage. Okay? There is an area attached to the technical definition. And that area relates to where is the charge passing. For instance, think about charge going through a wire. The area we're thinking about is how much charge passes into the wire. And the wire has a cross-sectional area. So there's a piece of wire. It's got some kind of an area. Some Q goes in. How much Q comes out relative to how much Q goes in based on your lab study? The same. If these two Qs were different, what happened to the charge? Maybe it got blocked up in there or something. And if it did, this thing would build up a static charge. If circuits built up static charges, then you might get shocked from everything you touched that was electronic. That doesn't happen because the charge in is the charge out. You don't build up these static charges in current-based electronics. In general, a complete circuit is needed for current to be maintained. We wouldn't continually have the same number of charges passing through the door if you guys were carrying the charge, unless we went over into 122 and walked around here and went back out again. And then maybe we could have a steady current. Otherwise, without that, we don't have a steady current. We don't have that complete circuit for the current to be maintained. Riley and I were talking about this in lab the other day. Probably things were nuts. But it's the way physics describes the topic. I think historically there was a lot known about circuits. When were the first electric circuits invented? I don't know. When were the first electric lights installed? Thomas Edison, things like that. 1800s, probably. Mid-18 to late, was there electric circuits in the Civil War? I don't know, I doubt it. But probably not long after we started having electric light bulbs, electric circuits of some type. When did we discover the electron even existed? That was J.J. Thomson in like 1918. And so circuits were being built and utilized before science even knew there was such a thing as an electron. So if you don't know such things exist, how do you decide what's actually happening in that circuit? Original circuits were probably very much practical based. How can we make electricity happen? It's the idea of the battery. The battery was invented in the 1700s, I think, by Alexander Volta. So the point is, we didn't know what was actually happening in a circuit for quite some time after we had the technology going. And as it turns out, we were wrong. We, meaning the physics community. The physics community built all of their discussion and theory on the idea that positive charges leave the high voltage end of a battery, travel around the circuit, and come back to the low voltage end. And nowadays, based on something called the Hall experiment, which I think was in the 1920s or 30s, we know that it's almost always electrons that carry currents, not positive things. So what's really happening is electrons are leaving the negative end of that battery and going the other direction and coming back to the positive end of the battery. But too bad, we've already set up our way of analyzing. I don't know why physics hasn't changed it, but they haven't. Maybe it's simpler, I don't know, to think about positive. There's something, positive charges are easier to make a gravity analogy with than negative charges are, I think. Because positive charges, even if they're imaginary in your head, go from high potential to low potential. So do masses. They fall from high potential to low potential. And because of the way we define things, electrons move from a low potential to a high potential. And that seems kind of backwards in some ways. So, I don't know. That's the way it happens. So I will almost exclusively talk about conventional current, which means I'm forgetting that electrons exist. I'm pretending that positive things move through a circuit. There's no difference in the physics, whichever we understand. Electrical engineers made the choice to do it right. If you take an electrical engineering course, they'll talk about negative charge carriers. But physics tends to not. And doesn't technology usually precede science? I think it does. I at least have heard the apocryphal story that once X-rays were discovered that, probably in the 1920s or 30s or something, you could go in an expensive department store and put your foot under a fluoroscope and wiggle your toes, before you bought your shoes, and see the bones in your feet. Oh, isn't that cool? Yeah. So I wonder how much radiation-induced cancer people got, right? But their feet in X-ray machines and like that. Okay? Nowadays, you go to the dentist, and they're going to give you this tiny little zap of X-rays up here, and they can just lead apron over your body, and they leave the room.
Yeah.
Hey, if you're leaving the room, I'm leaving too. Why is it safe for me to be in here? So again, the technology of seeing how to make X-rays certainly preceded our understanding of them. And one that's very much in my interest, the best violins in the world were made probably in the mid-1700s or so. Antonio Stradivari, Giuseppe Guarneri, so forth. Some of those fiddles sell for over $1 million. Okay? But it wasn't until about the 1940s or 50s that people started making violins according to good sound acoustical and physical principles, and started making some instruments that pretty much rival their quality. And so Stradivarius didn't know why he made the fiddle the way he did properly, but he had enough intuition that he just made something that was just incredibly good. And nowadays, most people think they can reproduce that quality. They do that with blind testing. I mean, even a lot of professional violinists can't tell which instrument's being played if you want to. So there's a mystique. I don't Stradivarius, I must be better. There's a mystique involved with the brain. Anyway, all that because negative charge and positive charge. Okay, some typical currents. What is an ampere? Well, an ampere, I don't know if I even said that. You have 1 coulomb passing by every 1 second is called 1 amp, or ampere. Is that a lot or is that a little? I don't know. Depends on your reference rate. 1 coulomb is a lot of electrons. It's 10 to the 19th electrons, which sounds like a lot until you realize that that's roughly a micromole. So is that a lot or not? Well, here's some typical current values. The lab that you did and will be doing. You recall the numbers you were seeing for current, it was typically around 0.2 amps, I think. And that's what's typical in a flashlight bulb kind of circuit, is an amp or less. You have currents in the neighborhood of milliamps running around your body. Okay, that's how your nervous system works, that's how your heart beats, and so forth. So what happens if suddenly some amps of current are interjected into your body? Which current does your heart pay attention to? The milliamp or the amp? And the amp, and so your body goes haywire with too much electricity. You've probably seen people in movies at least or something in the process of electrocution and their bodies are jerking around all the way. That's going to happen. Okay? Was it Volta that did the frog leg experiment thing? Right? Hook up a battery to a dead frog's leg and he's still, and the head been dead too long. But he can still make the leg jump, still make the nervous system fire with some pretty small currents. So large currents are incredibly dangerous to humans. And amps are very dangerous. And yet there are amps of current around us all the time. Okay? The circuits in your house carry 20, 30, 40, 50 amps of current. And so you've got to be a little careful messing around with household electricity. If you have an electrical socket go bad, you need to be careful changing that socket out. I mean, I know people that change them live. I certainly don't. And I don't trust you to do it right. Some people do. Or you do it wrong, and you definitely electrocute yourself. Your car circuit, particularly the starting circuit, can have hundreds of amps going on in the starting process. And you've got to be really careful with car electricity, particularly for the starting circuits. The process that goes on in the sun, hydrogen atoms are being fused into helium atoms. But in the process, it liberates many electrons. Those electrons flow out away from the sun. That's current, that's moving charge. There's about 1,800 amps of current reaching the Earth continuously, reaching the surface of the Earth. Okay? Well, why don't we build up a big static charge and just zap each other all the time? There are other mechanisms that involve removing that current, but to me, that's part of the design of this whole system. Is yeah, God created a sun to give us light. That's Genesis 1:3 or so. But nobody ever talks about, yeah, but he made an awful lot of electric current at the same time. How are you going to deal with that? And yeah, it's nice having light. What are you going to do with all that amps of current that also created to create the light? Well, he set up a system for the Van Allen radiation belts. That's part of the process. And all kinds of interesting things that go on in connection with let there be light. Maybe we should change it, let there be light and current. Maybe that's what that Hebrew word really means. Lightning bolts. Yeah, go tell the Bible prophet heresy expression. Greek, who needs Hebrew? Just need some good physics. Integrated circuits, like running your cell phone, that's probably microamps and maybe even smaller. So I don't think you're in danger of getting electrocuted from your cell phone. Probably not, because of the very low currents involved. Well, how do you make current happen? Remember my initial little discussion up here. You make current happen because you're moving charge. So you got to have a force or a field or a potential. We're going to talk about it in terms of potential. So let's take a wire like this one, hook it up to a battery. You've seen the symbol for battery now in the lab. So this is the high voltage end of the battery. This is the low voltage end. Maybe call this 0 volts. And this is, well, you were using 1.5 volt D cells. We'll do something with power supplies this week and use 3 volts or 4 volts. Let's put in some number there. 5 volts. Here's a connecting wire, connecting wire, connecting wire, connecting wire, connecting. That means this is a 5 volt spot. Here's a 0 volt spot, connecting wire, connecting wire, connecting wire, connecting wire. There's a 0 volt spot. To do that, you apply a potential difference to something that has charges that can move, like a piece of conductor wire. There will be current happening. There will be a charge flow from the high, conventional charge, conventional current. There will be a charge flow from the high voltage to the low voltage. There's a relationship between the voltage and the current. Take a wild guess. What if there's more voltage? More current. Yeah. More voltage means a bigger electric field, a bigger electric force. You're going to move more charges per unit time. And so a bigger voltage means a bigger current. So I put that first statement up there. It's really too mathematically precise, okay? Because I'm implying that it's a direct proportion by saying that. I haven't justified that yet. All we've really said is bigger voltage, bigger current. Smaller voltage, smaller current. Some of you probably did that in lab with the batteries and the bulbs. You decided that one battery wasn't making the bulbs as bright as you wanted them to be. So you put 2 batteries together, and in essence you're putting a 3 volt potential difference from that. Everybody do that? Use 2 batteries most of the time? So it was brighter. Okay? You were making more current because you had more voltage. Well, there's something else that influences how much current besides the voltage. And this is not a mathematical statement, it's just a general statement. The current also depends on what material this is made of. Light bulbs, this is made of mostly a piece of tungsten wire, which is what glows. The diode that you used in that first lab, if you hooked it up wrong, it didn't light. If you hooked it up right, it did. It had some sort of a interface between 2 types of semiconductors. One way allows charge to flow and the other way doesn't. So there was a difference in material, there was a difference in current. when you put a piece of wood or plastic or something here, you got so little current that you said it wasn't conductive because the bulb didn't light up. So not only does bigger voltage make for a bigger current, but the material influences the current too. Okay? We're going to parameterize that material property by something called resistance. That's the electrical property that assigns a value of some type to that material. You know, you get the handbook of chemistry and physics, and you can look up in the index and find out something about what's called the resistivity of different kinds of materials. Copper versus iron versus lead versus nichrome, kinds of stuff has different resistivities which feed into this number called resistance. Well, think about it for a minute. Resist. What's that mean? Against, limit, prohibit, something like that. So the idea here is that if a material does not allow very much current to flow, if I is small, then R is big. Big resistance, small current, small resistance, big current. So what kind of materials have low resistances? What kind of materials allow bigger currents to flow? Conductors. Conductors will typically have low resistance. Non-conductors will have much higher resistance. Well, if we put these two things together, I is proportional to V, I is proportional to 1 over R. Okay. Just like we've done in the lab many times through the course of the year, you can say that I is then equal to V over R with maybe some other constant in there. That other constant typically is related to the units that are involved. Well, it turns out that we need no other constant. The units, the resistance units are defined in such a way that there is no other constant. This is the relationship that we have. If you apply a voltage, so let's take a piece of material, and I apply a voltage across the two ends by means of a battery, there'll be some current flow, and I can define the resistance of that piece of material by taking the voltage divided by current. Let's solve that equation for R. R equals V over I. Units would be volts over amps. And volts over amps have their own name. It's called ohms. I think a German Friedrich Ohm, I believe is who that's named for, so I probably studied the initial ideas that turned into circuit analysis. And ohms have a special symbol. It's a capital omega from the Greek alphabet, so that kind of horseshoe looking shape. I don't know, do any of the units have special funny symbols like that? I mean, meters is little m, kilograms is kg, grams is little g, and so forth. But for whatever reason, ohms has that funny looking Greek letter symbol. Yeah, good, we know. Awful easy to confuse ohms with zeros, I suppose. Anyway, that's what it's there. Let's solve this again for the V. Well, I might as well just show it all three ways. This is kind of the key equation of circuit analysis. That's the one we'll use the most. That's called Ohm's law. It's unfortunate, I think, that it gets the name law attached to it. Because there are many, many materials that don't obey that don't follow that rule. There are enough to do, but it's still the fundamental idea of circuit analysis. But when you think about a physical law, Newton's laws, yeah, those are very, very broadly applicable. Okay. Newton's law of universal gravitation, very broadly applicable. Coulomb's law, very broadly applicable. Okay. Ohm's law, okay, but it's not in the same caliber as those others. Plenty of things don't obey Ohm's law, in the sense that the resistance is not a constant. And light bulbs are one. Light bulbs have You can't really say what's the resistance of this light bulb. It'll have many, many different values. There's a little thing called a diode that you used in lab. What's the resistance of a diode? You can't really quote a number for it. On the other hand, there are lots of things that you can. You can go to the parts store and buy a 30 ohm resistor or a 2000 ohm resistor, and it will have that number of ohms all the time. Okay, now let's see what do we do from this. Yeah, this is kind of just amplifying what I just got done saying. Let's make a little lab experiment out of this. Let's take a certain fixed piece of material and not change it. And let's apply a voltage and see how much current we get. In fact, you'll do this in next week's lab. Take some piece of material, apply a whole bunch of different voltages, get the current, and then let's plot it. I versus V. For many things, this will turn out to be a nice straight line. Why should this line go through the origin? I think that's a physics question. How much current do you think you should get if there's no voltage applied? Zero. Okay? Yeah, so you really want that relationship to obey that sort of idea. It takes some voltage to cause current. Okay. If this is the kind of graph you get, that's a straight line with no y-intercept, so it looks like y equals mx, except what's on the y-axis? The current. What's on the x-axis? The voltage. Well, what do you get? I is equal to v times 1 over r. That means the slope of this line is related to the resistance. It's a reciprocal of it. So if you get a nice straight line, then you know that material has a constant resistance. You can talk about its resistance. It doesn't change from condition to condition. This is more like the graph you would get from a light bulb down here, where as the voltage increases, the current doesn't grow at the same rate all the time. And so you get some non-linear relationship. In one sense, and this is nice and simple, right? This is easy. This is easy to understand. To the electrical engineer, this is all ring. Because you can't really do much creative with that. But if you find unique materials that have unique electrical properties, wow, then clever people can exploit those kind of nonlinearities and come up with all kinds of clever things, like diodes. Why is a diode so clever? Well, it's kind of clever. It lets electricity go one way but not the other. That seems kind of clever. Combine a couple of diodes in the right way and you make transistors. Transistors are the core idea of how a microprocessor works. It's millions of transistors engraved in silicon on a chip. Transistors is also how you make amplification. Like literally an amplifier in a public address system or something. With transistors in that, which are not going to have this kind of current voltage graph. Transistors will have much more complicated current voltage graphs. So many electronic ideas are based on the fact that something created. But you know, like they say, you got to crawl before you walk. You need to learn some simple circuit ideas before you go on and take the electric circuits course, which is not. But that at least is there. Well, it would be a good time on Monday, I guess, to try to keep them problems. So we will do that.